Hey everyone, I have a very interesting problem for you guys today. So we have a glass window which is of width 1 meter and height 2 meters. It is 5 millimeters thick and has a thermal conductivity of 1.4 watts per meter Kelvin. We know the inner and outer surface temperature for this glass as well, so which is 15 degrees Celsius and minus 20 degrees Celsius. So they are asking us to calculate the rate of heat loss through this window. In the second part of this question, they are in a cold winter day. It is customary to use a double pane window where two panes of window are separated by air. So in such an arrangement, the air separation here is 10 mm and the thermal conductivity of air is also given. So they are asking us to calculate the heat loss in double pane window. So let us calculate the first part of this question first. So known parameters in this case is window geometry. So we know the cross-sectional area because we know width and height and we know the thickness of the window. Then we know the thermal conductivity for window which is kg. We know inner and outer temperatures as well. So which is T in and T out. So what we need to find here is heat loss through the glass window. So for this problem the schematic would be, so this is our glass window. It's This is 1 meter, this is 2 meters, and the thickness T is 5 millimeters, which comes out to be 0.005 meters. We know the inside temperature, which is 15 degrees Celsius, or if we want to convert it into Kelvin, then it will be 273 plus 15, which will be 288 Kelvin, and outside temperature T out is minus 20 degrees Celsius. So that would be 273 minus 20 would be 253 Kelvin. So, and also the thermal conductivity of the glass Kg is given as 1.4 watt per meter Kelvin. So the inside temperature is 15 degrees Celsius, outside is minus 20. So obviously the heat transfer would be from higher to lower temperature. So it will be from inside to outside. So what are the assumptions here? That first assumption would be it is a steady state heat transfer. It is a second assumption would be it is a one-dimensional heat transfer. And third assumption would be throughout this temperature range from 15 degrees Celsius to minus 20 degrees Celsius, we are assuming the thermal conductivity is constant. It is not changing with temperature. Constant K. So we can simply use Fourier's law here, which is Q equal to minus thermal conductivity multiplied by cross-sectional area into temperature difference divided by thickness of the body. So we know K is 1.4, area is 2 multiplied by 1, delta T which is temperature difference, would be 253 minus 288 divided by thickness would be 0.005. So if we solve this, we get 19,600 watts, or we can say 19.6 kilowatts. Now for the second part of this question, they are saying there is a double pane window and the space between the two panes of glass is separated by air. So that air space separation is of 10 millimeters, and they have given the thermal conductivity of air as 0.024. So if we draw the schematic for this, there is pane 1, then there is a air separation, and this is pane 2. So this separation is of 10 mm and the window pane is of thickness 0.005 meters or 5 mm, and same for this window as well. So to solve this problem, we need to understand a few concepts first. So if we like we know the Fourier's formula is minus k multiplied by a dt by dx, and so if we take the term Ka into denominator, so it will come as Ka. So this formula can also be written in this form. So if we consider this in electrical analogy, so the I current and voltage difference V divided by resistance R. So in the heat transfer case, Q is the current, dt is the voltage transfer which is driving this current, and this term dx by Ka can be called as thermal resistance. So now if we see, there is this temperature inside in this region, there is temperature outside in this region, and heat is conducting from inside to outside, as inside temperature is more, but first it has to conduct through this pane first, then it will conduct through this air gap, and then finally it will conduct through this second pane. So all these conduction processes are in series. So if we, just like we do in electrical analogy, so there are three resistances in series. So we will call it as a thermal resistance. So this is thermal resistance for window 1. This is thermal resistance for air. This is thermal resistance for window 2. And this is T in and T out. So thermal thermal conduction is happening from T in to T out, and just like we do in electrical analogy, we have to calculate equivalent thermal resistance, and as these are in series, so we will simply add these thermal resistances. So this will be thickness of glass divided by thermal conductivity of glass into cross sectional area. Uh, This will be air, thermal conductivity of air into cross-sectional area plus thermal conductivity of glass into cross-sectional area. So this will give us the equivalent thermal resistance. So if we put all the values in the above equation and calculate, we will get equivalent resistance as 0.212 and its unit will be, so we know the this it will be Kelvin divided by watts. So this will be the unit of thermal resistance. Now if we put this equivalent resistance in our first equation, so we know Q equal to delta T divided by R equivalent. So delta T for us is, and don't forget the minus sign here. So 253 minus 288 divided by 0.212. So if we calculate this, this gives us 165.1 watt. So when there was only one pane, we got the thermal like heat loss value as 19.6 kilowatts, and if there are two panes, we got the value as 165.1 watt. So if we compare the two values, we are getting almost 100 and more than 118 times difference. So there is so much heat loss we are preventing just by using two panes. So for some practical example, so let's consider there is a heater running inside the room, which is which we are using to heat up the room. So if there is only a single pane and the heater is running, so that heater has to put out 19.6 kilowatts of power. But if only we use two panes, then that power consumption reduces drastically, like 118 times, and it will come out to be 161.1 watt, 165.1 watt. So this this is the practical solution, like how to reduce our energy consumption. Just by using some additional material, we can reduce our energy consumption drastically. So, yeah, thank you for watching. Please like, share, and subscribe. Thank you. Bye bye.